Welcome back to the Health Physics Society's video series pursuing the truth and promoting transparency regarding the historical foundations of the current radiation protection philosophy based on a linear no-threshold theory for cancer risk assessment. I'm Dr. John Cardarelli, President of the Health Physics Society. In the fifth episode, we learned about Muller's best friend Edgar Altenburg and Stadler's colleagues Barbara McClintock, calling into question their early conclusions that X-rays induced gene mutations. The sixth episode reveals a doubling down of the linear no-threshold theory by proposing a biologically plausible mechanism that Muller called the single-hit model. He promotes cumulative dose as the best predictor for risk, and as a result, genetic mutations and risk become independent of dose rate. His students conduct studies to confirm his belief, and he even mentions one of them during his Nobel Prize speech. What he doesn't mention, though, may surprise you.
So did Muller then go on to formulate other theories of how this genetic mutation that he claimed was occurring?
Yes, he did, and he needed a new platform. A new way to just change the question and go at it from a different angle. And he came up with a creative way to do this, and it was fundamental to two areas. And it was looking at what was the best way to predict genetic risk? Was it through a total cumulative dose, or was it the dose rate? And this was very significant because Muller was a strong believer in LNT, and he wanted to be able to get down to a single ionization so he could prove his gene mutation hypothesis. And so by framing a question, well, what is the best predictor of genetic risk through these cumulative dose or dose rate, it gave him that vehicle. And so what he was with this total dose, and this is what Muller believed in, was total dose. It was like, I call it the piggy bank theory. Okay, in a piggy bank, if they still have them these days, you put a single penny in one day, and then the next day another penny, and just keep putting pennies in. Eventually, you come up with a certain number, and the total amount of money is the total count of pennies, and you string it out. It's really like a linear sort of a thing. And so when it comes to genetic damage, well, Muller believed that, like a piggy bank, every little bit of genetic damage was cumulative, and it just added up like a piggy bank added up. There was no repair. Like in a piggy bank, you didn't take out the money, you just kept it in. And so what happened is that there was cumulative damage, there was no repair, it was irreversible. And if you add those three things together, what happens is it becomes a linear dose response. And you can take that all the way down to a single ionization and a single really micro change in a gene. And so Muller thought that this was how it actually worked, that it didn't make any difference if you got mutation today, then you got the mutation a week, it would just add up.
So this was well before the knowledge we have now about DNA repair.
Oh, that's right. That's exactly right. This was circa 1938. He was framing this particular thing, and his view was that there was no repair, and so he could evaluate this by this dose rate total dose study. And so he attracted a graduate student over at the University of Edinburgh, and this graduate student was working with Muller's favorite, fruit flies. And so what Muller wanted this person to do was to take a kind of a modestly high dose of radiation given pretty much all at one time. And so that would be like a total dose. And then it would be enough to cause quantifiable damage, mutational damage, however they were going to be measuring it. And then take that same total dose, but just divide it out so that you give it prorated out over the course of the 3 or 4 weeks that the fruit fly would live. And so if you just gave a low dose every single day and it added up in total to that you gave all at one time, then you could see, well, whether Muller's piggy bank theory would actually work.
So you would expect to see the same amount of damage,
exactly,
whether it was spread out over a long time or delivered in a very short time.
That's right. And so this was, and if Muller could show that, then he would show the linearity of the dose response, and he could bring damage down to a micro level, and it would really kill two birds with one stone. And so he got this student to do it. And so it sounds simple, but these are complicated studies to do. And you really need to have well-educated, well-trained students in genetics, in Drosophila genetics, and so forth. And so they went forward and did this study. And to my surprise, I mean, looking back on it, the student confirmed Muller's view that what Muller said was supported by the student's dissertation. And that was when you gave it all at one time, or when you divided it out over the whole lifespan of the individual, it didn't make any difference. You came up with the same amount of damage. And Muller's theory was supported by this dissertation. I can tell you, I mean, I wasn't there with Muller, but reading his letters and follow-up communications and articles and so forth, that this was a big breakthrough. At least that's how he presented it. And so this, in many ways, it got Statler off his back. And he could breathe free, and he had a whole new set of arguments, and he was moving in a direction that Statler wasn't going. And
were they still identifying the mutations at this time by visual inspection?
Yes, it was entirely visual. It was circa the early technology hadn't changed. Muller was following the same basic plan, but with a different study design, a different kind of a question to try to answer. And so what happened was that I got, in my retrospective way of looking at things, I got to look at this student's dissertation. And I got not just the dissertation, but I got all the letters between Muller and the student. And I got the copy of the comments by the committee to the student and how they responded. And in some ways, the student was very communicative. And Muller was also back and forth, but it was very revealing as to what went on. Now, I would say that when they published the work, Muller made the case that just what I had said before, that this student proved his case. And in fact, when Muller was to get his Nobel Prize, which was in 1946, a centerpiece of justification for this Nobel Prize was this student's dissertation. It not only, he not only had discovered mutation, but this student had supported the gene mutation interpretation, but also supported the LNT. And Muller used it as a vehicle to discredit the threshold model. And in fact, in the Nobel Prize speech, which was December 12, 1946, Muller specifically states the student's dissertation, names the student's name, which must have been a tremendous thrill for any graduate student. And based upon this particular person's study, there is no longer any scientific standing for the threshold model. And we have to shift over to now a linear dose response. And Muller made this claim right in front of the Nobel Prize audience for the world to hear. It was a centerpiece. Now, the interesting thing is that I got all this information. And so I had a chance to look at it. Well, really, how good was it? Okay. And
you looked at the actual study that the student did.
Yes, I have copious extraneous details.
With data.
With data, what was published, what wasn't published, the student's self-doubts, the advice that Muller didn't give, the criticisms from the committee, and saw how it all played out and whether what was published matched reality, things of that nature. Now, as it turns out, the study has a gigantic set of potential flaws. It has real flaws. And I would start by pointing out that the study really had an inadequate number of flies within it. It was a very small study. It had very poor controls, what I call technical controls, like the temperature control, which is really important for when you're rearing Drosophila, was highly variable. He used a different type of temperature control between his controls and his treatment groups. They ran 8 experiments. In this 4th experiment, the entire temperature control failed, and that experiment failed. the student was not very skilled in working with Drosophila. And Muller wanted to have, as any experimenter would, one variable in a study. You're testing changes in the radiation and the concentration times time interaction that he was looking at for this dose rate study. And so what Muller gave to the student was an assignment. He taught the student how to cross-breed his Drosophila so he could come up with homozygous or genetically pure substrains. And so, and I have in the letters, the student writes to Muller, he says, "I've tried hard. I'm not doing nearly as well as what you want. This is really difficult. I can understand why you thought this might be a bit over my head. This is I hope I get to doing well at some point on this." And I look into the records, right? And I find that, and this is not reported in the dissertation, it's not reported in the published papers, but I have it in the data. And what happened, and the data matches up with all the numbers that get published. And what happens is that he created a whole series of what I call subclones, subspecies, substrains, whatever word you want to use, and that they were genetically different. It wasn't like you were just having, you know, all these fruit flies of the same genus species, and then you were just going to vary the amount of radiation. But he actually had multiple different, what I call substrains of his fruit fly, and they were differentially distributed amongst the treatment groups. So the control had you know, one proportion, it might be 50% of something, and the other one had only 20% of it, and that was so introduced.
So the control group didn't really match the treatment group.
Exactly, and to me, what was really troubling was that was never reported. It was masked, hidden from the literature, and also what happened was that he measured mutation, but he measured some other genetic changes, such as inversions of chromosomes or other types of things. And what happened was that in one of the first experiment, some genetic adverse effect, it didn't at low doses, it didn't show any effect. There was no treatment effect, and so those data were not reported. And so they were selective in what they reported. They didn't show other kinds of information. Halfway through their study, this is hard to believe, halfway through their study, they changed their Drosophila model, and they didn't justify why. They actually changed the model, and the model had a background mutation rate of only 20% of what the other model had. And yet they combined all their experiments together without justifying that. Also, what happened part of the way through the study is that they ended up changing the diet that the female was on. And that may seem very trivial to people, but they're doing a study where the diet determines when the female goes into laying eggs. And in that particular study, they had fertilized females and wanted to store the egg within what's called a spermatheca in the female, and then later on, at some point, change the diet and have eggs produced, and you could check for genetic effects, but the animal is being exposed to radiation all the time. What that does is allows you, in a technical sense, to study the effects on young sperm or old sperm, and it really relates to how much radiation they get. But as a sperm stays in the spermatheca, it naturally gets more mutations. The study becomes more complicated, is what I'm trying to say. And they never clarified that. They treated them all the same. And in the course of this, I found, and I'm going into this in some detail with you, because I found a lot of problems with their study, a lot of problems. And I'm only just scratching the surface now. It's me going back and looking after all these years, and I find that Muller and his graduate student never mentioned any of these, or most of them were not mentioned.
Thank you for watching the 6th episode on the historical foundations of the linear no-threshold theory, where we learned about the study that Muller attempted to use to support his gene mutation interpretation and support for LNT. and to escape Stadler's unrelenting criticism of Muller's reverse mutation proposal. Muller cited this study in his Nobel Prize lecture and challenged the continued use of the threshold dose model that was in place at the time. However, in episode 6, Dr. Calabrese presented an alternative view, one that challenged the quality of this study, showing numerous flaws and questioning its conclusions, and the judgment of Muller to highlight it in his Nobel Prize lecture. The next episode is set in the Manhattan Project era, when the government pursues a deeper understanding of biological effects of ionizing radiation. The HPS is a trusted source of radiation information. We're a scientific organization, and as is offered with a scientific peer review process, viewers are encouraged to send comments or suggested corrections to factcheck@hps.org, and be sure to include your sources so that we may correct the record if necessary. If any changes are made, they will appear at the end of this episode. Please visit our Ask the Experts website to ask questions or seek answers to common radiation-related questions, and view our fact sheets. We also have official position statements that can be found on our website at hps.org. Finally, if you wish to join the Home for Radiation Protection Professionals, please visit the link below. We welcome you.